to keep our little community working together. I got often asked by people how many people in the world work on insect navigation, and it's obviously hard to say because it's kind of a viscous continuum. But today we can see that it's something like 33 people very interested, which is not too bad. Now we have a good idea. But yeah, thank you very much. Can you see my screen? The presentation? Okay. So I'm going to speak today about works that we've been doing with Léo Clément, Sébastien Schwartz, and Florent Lemoel. Behavioral work on these little cataglyphis velox in the field in Seville, which has been inaugurated by Mike Mangan and Barbara Webb like more than a decade ago. And almost every year, I think there has been now a researcher going there in this field doing experiment with these cataglyphis velox, which are really nice ants. Their bites is not painful at all. You give them a cookie, usually they take it and are motivated to go home, which enable to make a lot of very simple experiments very easily by just displacing them. And I'll try to speak today about some experiment we've made to try to understand how root learning is learned at the first place. So these ants, of course, are very well known to get these idiosyncratic roots, like many other solitary foraging ants. One of the experiments we've done in the field in the last year was something that we do in most experiments, is that you delineate a root with little barrier. The little barrier are mostly here to incite the forager of this nest to find the food here and to prevent invaders from other nests to steal their food, and because that creates fight in the feeder, which is not very nice. But once you have that, usually really quickly, you will have several individuals that will go and try to find food in your feeder. And they will shuttle back and forth and learn this route very well. And you can go 100 meters further and have a typical test field, which is a place that these ants don't know. And therefore, we used this test field to try to know how quick they would learn a new place of the world. So to do so, we have our well-trained ants, and we capture them when they are leaving the feeder back to the nest, but we grab them just while they leave the feeder. They have a cookie in the mouth, they want to go home, but we displace them into this unknown test field. So we know that in theory, they have these path integration vectors that should pull them using notably celestial cues here towards, let's say, the south, which is what you see if you release your ant. You see that she goes to the south. To give you an idea, here the route is 8 meters long, and here the test field has a radius of 3 meters. We grab the ant here, we put her back in her route, and later on, we grab again this same individual as it arrives at his nest. So now it's so-called the zero vector ants in the sense that he can no longer use path integration. We release him for the second time on this test field. And we were pleased to see that it was kind of recapitulating already a route. Here, it doesn't have path integration information. Probably he has learned views during his first trip. If you do that with many individuals, you can see that as a zero vector ant, it tends to show that they've learned the route. And here it's a little quantification to check if the route of an individual is similar to its own routes during this first full vector trial. And yes, meaning that they didn't just learn to go roughly south, they actually learned an idiosyncratic route here in one trial. Very efficient. So in this particular experiment, we replace the ant in a familiar route, and she enters the nest. This could constitute a reward that makes and crystallize the route memory. But we tried several conditions. Instead of releasing in the nest, these are the same results that you've just seen. We can release them in the familiar route, but not letting them enter the nest, or even release them in another unfamiliar test field, grab them again, and bring them back as a zero vector ants for the second time on the test field. In all those situations, the ants learn that they've learned the route. So it looks like there's no real need of the reward of entering the nest for them to crystallize and use these route memories. Can learn in one go, and they are really keen on recalling it, even if it leads nowhere, literally, because in this condition, there was no apparent reward of going home. Well, it could be that all these ants were full vector, and therefore were using their path integrator vector, the fact that they were going down the path integration to learn. So we made another experiment, which this time we took ants as zero vector ants and released them for the first time on this unfamiliar test field, where they search as expected. Eventually, they reach the 3-meter radius limit, on which point we take them, let them back on the route, and bring them again for another trial as a zero vector ants. And we are really surprised to see that during this second trial, it didn't look like a systematic search anymore. There was a lot of this loop, as if the ants were actually redoing a route that is similar to the first systematic search, but not necessarily exploring different area and rather getting stuck turning into loop. If we make our little quantification as well, we can see that the second trial of each ant is mostly similar to their own first trial. So somehow they've learned a route which was here not very efficient because the route was based on a search. They don't recapitulate the search in the correct sequence, but they get stuck in loops that they've done before. So it looks like they don't really need to go down their path integrator to learn. It looks like they are a compulsive learner that just would remember anything they've done and redo it again if they see the same things. Keep in mind that these are really unnatural situations where we've put the ant in unfamiliar test field as zero vector ants. In natural condition, this shouldn't emerge, right? There's a path integrator. But the question is, do they learn continuously? And that's a bit weird because, as you've seen before, now we have enough evidence to know that the ant seems to learn view in a rotationally dependent manner. Visual recognition depends on the gaze orientation. That's why they may scan around or even oscillate along their path to expose their gaze to many directions. So how could they learn continuously? When exactly do they learn? In which orientation do they learn? A typical model makes them learn while facing the route. There was another model that we developed, which was based on this evidence. We made an experiment in the field where we had these ants on the trackball, where they were fixed in a given position and gaze orientation, but they could rotate the ball below their feet, so we could record if they try to turn right or left. When we put these ants on their familiar route, we can see that when we force them to look, for instance, left from their route, they will try to turn in the correct route direction and vice versa. It looks like whatever orientation you show them, they know whether they should turn left or right. We've done this in 2 species. If you release them, the ants in unfamiliar terrain in the same compass and formation, it looks like it's random at the population level. So there is a visual recognition that is not necessarily happening when the ant is facing its route. What's interesting, if you look here, the percentage of time the ants will spend turning in their favorite direction, whether left or right, we can see that even when we make them face the actual route direction, they will actually, individuals will actually decide to go left or right and stick to it for 80 to 90% of the time, as if a view was rather telling turn left or turn right, but not necessarily turn straight. So at the population level, when you make them face the route, you have as much individuals that turn left or turn right, which make 0 in average, but each individual has his own little decision. It looks like the system is made to tell them to turn left or right. This led to this idea that maybe they store several memory banks of views when I'm offset towards the left and the right. And depending on which one is currently the most familiar, it would trigger a steering towards the left and the right. Still, the question is, how is learning control? And actually, part of this response, I think, is about how they steer. So there is now accumulated evidence that many insects use central complex for steering, and as well ants, and in the end, visual recognition from the mushroom body could send signal to the central complex, which in turn takes control for steering. We tested for that by using the classic mirror experiment with the ants on the ball. You arrive with a mirror, the sun appears in the opposite direction in the sky for the ants, and you look at its response. What you can see if you have trained ants to really turn right when they arrive at this intersection and when they face this direction, you have them on the trackball, they cannot rotate, but we can see whether they try to turn left or right. In this case, they all try to turn right, which is their familiar route direction. But if you mirror the sun, they suddenly shift and start to turn left. Even though the evidence is that the terrestrial cues tell them to turn right, there will be a moment where they will reverse their decision. This is true also if you train ants on a straight route. So you put them straight on their route, you will have half of the ants who prefer to turn left and the other half to turn right. Here we that would just shift so that they all go in the same direction. But when you arrive with your mirror, these ends also shift direction, even if they face their route. So it looks like the decision to turn left or right somehow transiently goes in the central complex, where it will be guided by celestial information. So that led to this model where you have views recognized in the mushroom bodies that goes in the central complex that will use celestial cues for steering, acting as a buffer. And a simple model shows that it's quite robust, and you don't need to learn you a specific angle on the left, on the right, whether when you have your memory banks roughly biased on left and right, you will have your central complex outputting a very nice response. But how is it learned? Well, actually, there is a lot of motor feedback. Drosophila studies shows actually when you look at whole brain imaging of activity of neurons, when the flies start to turn left or right or go forward, you have the whole brain and the dopaminergic systems that lights up. So it looks like there's loads of dopaminergic motor feedback. The simple idea would be that if you try to turn left, right, you turn left, but you'd also use that to memorize that these views are made for turning left. At the beginning of your career, you'll use path integration to drive your way. This path integration will make you turn right or left to align with your goal. And you can, in the same time, associate whether this view tells you to turn left or right. You categorize your memory bank based on really your steering system. So that could explain how these ends, homing ends, use homing path integrator during homing to categorize view. But there's a lot of evidence as well that during their way out, while they search for food, during this moment, they also learn information for their homing behavior. So there's a kind of cross-motivation memory, notably in the learning walks, right? During the learning walks, here you have the ant who execute a learning walk. She's not guided by path integration, otherwise she would just go to her nest. So she must be guided by other system. However, we know that path integration is running in the background, and the information that path integration could tell is that whether your nest is left or right, if you would be homing. But you could use this information now to categorize your view, even though you're not using it currently to home. So while you're, for instance, displaying your learning walks, you could learn based on your path integrator whether you should learn on your left or your right memory bank. And if you do that at the end of your learning walks, you have two nice memory bank here that are sampled for kind of all position around the nest. And then if you're released, you could compare your current view with both memory bands, exactly like we've seen before, to tell you whether you should turn left or right. And that actually creates quite robust homing in the model. Now the question is that, yes, this is during learning walks, maybe, but are learning walks spatial? Is path integration used for categorizing view only during learning walks? So we did an experiment to test for this, where we had the ants being experienced to a route like before, and we grabbed these ants just before they reach their familiar feeder, but before they get the food. So they are still wanting some food. We put them in the unfamiliar area. So we know they have the path integration homing vector that points down. However, they are not using it. If you look what they've done, we gave them 30 seconds. What they've done is basically trying to search for food here in this new environment because they still want to get a cookie. They don't try to go home. However, during this moment, they could still use the path integration information to try to categorize this view that they're experiencing while searching for their cookie to actually tell them if they should turn left or right, if ever one day they want to go home from this location. So once we get this 30-second glimpse, we put them back in their natural, their familiar route. We now grab them as zero vector ants and put them for the second time. And they seemed indeed biased towards where should be their nest according to what the path integrator told them when they have witnessed this area for 30 seconds. If you look at their initial bearing, it's very significant. They go down. As a control, we did the same, except that these guys were released for their 30-second glimpse somewhere else in another unfamiliar environment. And they were tested on the same test field than this first guy. You can see that in a completely foreign test field, the zero vector ants actually go the other way. They tend to what we call backtrack, doing backtracking. So it looks like this 30-second glimpse was enough for these ants, even though they were not trying to go home, to tell them, if you want to go home here, now that you have a cookie, it's this way. So it goes in the same idea that for the learning works, path integration may be there to orchestrate the categorization between left and right view in case you want to use them later for homing. So as an overall little conclusion, if I take back this little scheme that was actually taken from a Drosophila work in Heisenberg for olfactory motivation, and that in the review we worked with Barbara Webb, we just plugged the vision instead of the olfaction. You have these mushroom body output neurons, and we assume that you need at least two, one for the memory of going home, one for the memory of going out for food. Well, with the idea that they learn left and right views, at least you need to double this M-bond, a memoric bank for the too much to the left and too much to the right gaze orientation. And also what we've seen is that while you're going out, you learned views for going out, but you also learn view for going home, as we've seen. So it looks like there's a lot of parallel memories that are formed in the same time. While the ant is going out, she's learning how to go out, but also how to go home. And when the ant is going back home, she learns view to go home indeed, but also view to go back to the feeder, which I didn't present here, but it looks very symmetrical in our results. How am I going with time? Do I have 3 minutes more?
No, I'm good.
Okay.
3-4 minutes. Yeah.
Perfect. So then I will jump the acknowledgement for a kind of switch topic, because I thought it was interesting and timely to mention this phenomenon that I guess most of you are familiar, is that if ants are trained to a root corridor and you make sure they've never existed this root corridor in their little foraging career, and you release them on the side, these ants tend to converge towards their root until reaching the root and then go back to the nest. And that's interesting because a typical model, like I highlight here a recent very nice work actually from Sussex of Amani that made several models and saw that indeed there's a problem, because in the typical model that we use, where we use just rotational IDF to try to see where to go, if you release the agent on the side of the root, it tends to go parallel, which is completely natural. Learning left and right views doesn't solve this problem. You get parallel root exactly the same way. So you need an additional thing that explain how you converge towards the root. And in the last 15 years, there have been many hypotheses how it is. In the recent paper of Amani, there's a very nice one, which is about cast and surge, inspired for olfactory navigation, where basically most of these models exploit the gradients that you have of familiarity, because as okay, your best familiar views will be parallel to your root. However, as you get closer to the root, familiarity can increase. And you could use this short-term memory of looking how familiarity change across displacement and sort of using this to direct yourself towards higher gradient of familiarity. Several techniques like that. So exploiting a gradient across space. I just cited here, I'm sorry, but there's many people who have very nice solution of how to do convergence. We did some work about convergence to see if they needed this familiarity gradient by using our trackball. Same than before. The good thing here is that the ants cannot move across space nor direction. We just show her one view. She can move a little bit the head. That's it. And from there, can you know where to go when you relieve off your route? So if we relieve the ants on their familiar route, we have the same result that before. The typical signature, they try to turn left when the root is on their left, and they try to turn right when the root is on the right. Now what happens if we release them off root? Well, you can see here in blue, there seems to be a signature, but it's not the same as the red one. In black, it's exactly the same data than the blue. I just shifted them 90 degrees. So that's now the basically symmetry point, as if the goal point was there instead of down as it is usual. And you can see now the black curve kind of looks similar than the red curve. It goes in this direction. So everything looks like when she is here, she knows that she needs to turn this way. If she's oriented towards the blue arrow, she will actually try to turn right to go towards this black arrow. She hasn't sampled anything across direction. It's the first time she sees this view. She doesn't even sample much direction. She just has the possibility to move the head a little bit. And that seems enough for her already to know where to go. So doesn't mean that using the gradient is wrong. I guess there is this going on as well, but there must be as well an exploitation in the current view, so probably exploiting the actual structure of the panorama to deduce where is the actual direction of a route. And that would be it for me. Of course, I thank everyone which across the years helped me doing all these experiments, and of course my main mentors. as well as the recent collaborators. And thank you for your attention.